Welcome to BKW Physics. I'm Mr. McConnelly, and we're continuing our talk on magnetism. We're going to talk about the third left-hand rule today. So we've done the first and the second left-hand rule, and just to recap real quickly, the first left-hand rule, your thumb followed the electrons, and your fingers curling in the natural direction showed you the direction of the magnetism around a wire, a current-carrying wire. In the second left-hand rule, we had a coil of wire called a solenoid, and we followed the electrons with our fingers this time, letting our fingers naturally wrap around the coil, and our thumb indicated to us which direction the north pole of the solenoid was. Now today we're going to jump into the third left-hand rule, and on the third left-hand rule, one situation is if you had a horseshoe magnet, and then you had a circuit, an electrical circuit, where the wire of the electrical circuit ran between the north and the south of the horseshoe magnet. Just for instance, this is one scenario. And you might think, this is far-fetched, but actually there's a lot of application to this. So, if this were to happen, there would be an interaction here. And the wire would actually experience a force. So this third left-hand rule, what it's trying to find for you is it's trying to find a force, or the direction of the force. So here's how it goes. The first thing you do is you take your thumb and you follow the electrons again. So, looking at our picture here, the electrons are going to be traveling this way. So remember, we're using our left hand, and we follow the electrons. We follow the electrons. Follow the electrons this way. We follow the electrons with our thumb. Easy enough. Step number 2, our fingers. Point in the direction of the magnetic field. So in other words, your fingers point I don't know how to say it, I guess towards the south. That's the way I'll phrase it. Because remember the magnetic field, when we had backing up a couple lessons, when we had a bar magnet north to south, and we drew the magnetic field went from the north to the south, correct? So what I'm saying is with your fingers, point your fingers in the direction of the magnetic field. Like, follow the magnetic field with your fingers. So in essence, your fingertips, your fingernails are pointing towards the south. Fair enough? Let me erase that. So, here we go. Thumb is going like this. Now there's the north and the south. How do my fingers have to point? Well, my fingertips have to point towards the south, and my thumb is still going along with the wire. So my hand's kind of arranged like this. Can you visualize it? Can you do it yourself? That leaves us with the last thing. I'll just draw this. That's representing the magnetic field cutting across, so that's how our fingers should go. And then the last thing is your palm. We haven't used our palm yet. The palm of our hand shows the force direction. So, if I go like this, if I take my thumb and I follow the electron flow, if I take my fingers and I point them towards the south, or in the direction of the magnetic field, then my palm is left up. So the magnetic force that will occur on this wire is up. So what will actually happen is if you run a wire between a magnet like this and you turn on the power on the circuit, the wire will actually get pushed upward if it's a really strong magnet and a strong electrical flow of current. Otherwise, you might not see the wire move, but there is a force that the wire is experiencing. I can draw this differently though. Another example, I'll leave the rules right here and I'll just draw another example right here. What if, I won't draw it in 3D this time, what if you had a north and a south like this, and this is the information I gave you. Now first of all, some of you are saying, I don't even know what that means. So let's define what that X'd out circle means. That means that something is flowing into the board. And in this case, that something is electrons are flowing into the board. So when you see the X, it means into. And when you see a circle with a dot in the middle, it means out of or out towards you. So, we can see by this picture that the electrons are flowing into the board. We can see there's a north and a south, and we deduce that there's going to be a force exerted on this flow of electrons. So let's figure out which direction it is. Left-hand rules. Third left-hand rule. Thumb points in the direction of the electron. So, boom, my thumb is definitely going into the board. But notice the way I arranged my hand right now, my fingers are definitely going the wrong direction. So I'm going to have to do this, so that now my thumb is still into the board, my fingers are pointing towards the south, and my palm definitely shows force in the upper direction. So the force in this case is again upwards. Another example. What if we took this time and said, okay, we said this. You got a big north up here, a big south down here. And we said, someone is firing a beam of electrons, that's a beam of electrons, between the north and the south. Now, since it's a beam of electrons, it's individual electrons that are being shot out in a beam, they're probably going to be more susceptible, because they're so small and light, to being moved by this scenario. So these electrons, when they go between the north and the south, they're either going to get bent up, down, out, or in. And I want to figure out which way they're going to get bent. Because when I shoot them between here, they're probably going to curve one way or the other. And this is going to actually tie into other experimentation that we're going to talk about later. But for right now, here's what you know. You know it's a third left-hand rule problem. You see the scenario. How do you set up your hand? Well, your thumb goes that way. Your fingers have to point down towards the south, right? Your fingertips down towards the south. So this beam is going to experience a force which way? Out. And how do I draw that? Circle. I'll draw it real big like that. So these are going to get pushed out. And to be clear, I might want to label it force or put an F to show that the red mark that I just drew on the board indicates the force pushing out. Alright, now before we move on from this, there's one other thing that's not really a third left-hand rule, but has a lot of application, and I want to draw it for you, see if it makes sense. Say you had two wires, and these two electrical wires kind of running parallel to one another. Okay, that's two electrical wires running parallel to one another. And let's say that electrons are flowing this way on this one and the same way on this one. These are two separate circuits, two separate wires. you know that there's going to be a magnetism around these wires. In fact, we can quickly figure it out. Now, this is not a third left-hand rule. This would be, is it a first or a second left-hand rule? First, because it's just wires. So it's current carrying wires. So I would put my thumb in the direction of the electron flow, and I could pretty quickly see that there's some magnetism. I'll label it B to indicate magnetism. There's some magnetism flowing around the wire and flowing around the wire. Okay? Well, if there's magnetism around this wire and magnetism around this wire, eventually in the middle here there's going to be like a clash of magnetism, if you will. Can you see that? And because this picture is very hard to visualize, I'm going to change our perspective a little bit, and I'm going to look at it from the top view. So I'm going to draw a wire and a wire. And since the electrons, if I'm looking at it from the top view, if I'm looking at it from the top view, they're coming towards me. I'm going to draw it like that, indicating that the electrons are coming out towards us. And then, you know, because of my left-hand rule thing, I'm going to show that the magnetism is going around this way, right? So I'm using my left-hand rule to indicate that. And I can come out another layer here. And I can come out another layer here. So look what's happening right there in the middle. See that there's going to be a problem here? You got like clashing magnetism. So what happens when I go out a little bit further? When I come here, what's going to happen? So it's coming this way. What do I do? Well, actually, since the magnetism can't like fit between there, the magnetism is going to go, oh, whoa. Oh, whoa. See what it just did? And can you see that it just kind of joined these two things together? What do you think the net effect's going to be here? Since the magnetism of this one and the magnetism of this one kind of tied themselves together, these two things are going to experience what? They're actually going to be pulled together a little bit. So there's going to be a slight force. It's not going to be really big. But there's going to be a slight force that these two things are pulled together. Why is this important? Because when you run wires, like we recently had the play at school, or a concert, any concert, when you're running a bunch of wires because you got a lot of signals going from a stage to a soundboard or something like that, there's always a risk when you start running wires parallel to each other, because those wires are carrying electrons, the electrons make magnetism, and the magnetism affects the wire next to it. And what does that sound like when it doesn't do what you want? Squeaky. Yeah, that squeaky feedback. This effect is the reason why sometimes when you run wires next to each other, you get feedback. And you can show it if the electrons are going two different ways, you also have an effect. It's just like pushing apart instead of pulling together. Okay? So you've seen the effects that magnetism can have on wires and what it sounds like if you do it wrong. So today, physics.